Assalamu alaikum. This is lecture 6 of Information and Communication Technologies, and in this lecture we are going to discuss about how computers process information and different kinds of numbers, and mainly we will focus on different kinds of number systems. So here are the lecture contents. We will discuss few types of number systems which are commonly used by humans and one is used by the computers. So after the overview of representations of numbers, we will look briefly at the conversions of numbers between different types. So to represent a set of numbers, you must have a numeral system. A numeral system is a way of expressing numbers or using a mathematical notation for representing numbers of a given set using some symbols in a consistent manner. Ideally, a numeral system will represent a useful set of numbers, and these numbers may be integers or some rational numbers. And ideally, this numeral system should represent every number with a unique or standard representation. Numeral system will also represent the algebraic and arithmetic structures of the numbers. So in general terms, a number system is a manner of counting. For example, the number system commonly used by the human is decimal number system, which starts from 0 up to 9. However, there are other several number systems that exist, and we will discuss few of these in this lecture. For a computer, everything is a number, whether these are alphabets or numbers itself, punctuation marks, sounds, pictures, computer instructions. Everything is a number, and the number is represented in a binary format. So for example, here are some words are represented by our natural language here and a computer language in comparison. So every number system has a base or a radix. That means the maximum possible numbers that a system can represent. So radix is the number of distinct symbols that can be used to represent in a number system. For example, the base of the decimal numeral system is the 10. So as we can use the 10 symbols from 0 to 9 to represent numbers in the system. So four systems which we will commonly use in this lecture are binary, which has the base 2. That means we can only use two digits, and those two digits will be 0, 1. Another common number system is the octal, which has the base of 8. That means 8 symbols will be used to represent numbers, and the digits will start from 0 to 7. In the decimal number system, which is commonly used by the human, these represent a base 10, and these are the common numbers 0 to 9. There is another number system which is hexadecimal number system, which has a base 16 and which has the letters or the symbols from 0 to 16. So when you have 0 to 9, these are the same numbers or digits from the decimal system, and when you have to represent digits from 10 to 16, sorry, 10 to 15, you replace these with symbols of alphabets. For example, 10 stands for A, 11 for B, and up to F for 15. So this means that same number will have different representation in different systems. So 101 in decimal means 101, and it means 5 in the binary. So while 5 is the 5 in the decimal, but it is invalid in binary as the symbol 5 is not allowed. So again, if you recap it briefly, we have the binary number system, and in this number system we will have only two digits, that is 0 and 1. So if we use octal number system, these digits can be augmented to 7 because the base is 8, and for decimal this can be extended to 9. So the normal number system for human is the decimal number system. The decimal number system, which is based on radix 10, has 10 as its base. It is a numerical based the numerical base most widely used by the modern civilization. As you can see, there is a representation given as an example for a decimal number system in which a value is given in 1 point some millions, and we have a decimal point value and the fraction value is given afterwards. So for each of the digit in the decimal number system, we have representation from its 0 location to up to n. For example, if we have a number 4, 3, 2, 1, so our first number is located at location 0, this is located at location 1, this is located at location 2, and this is located at location 3. So each location converts itself to a weight. For example, if you are at initial location or 0 location, it will convert itself to the base power 0. Subsequently, 10 raised to power 1, 10 raised to power 2, and 10 raised to power 3. So on the other hand, computers use the binary number system, which has the base 2. That means the highest possible digit in the binary number system will be 0 and the lowest will be 1. So usually most of the information is used in on or off format, and which translates it to 1 and 0 respectively. The rest of the rules are similar as with the decimal case. The octal number system has the base 8 and the highest possible digit will be 7, and the lowest possible digit will be 0, and we have range from 0 to 7. The final number system, which is commonly used by the human, is the hexadecimal numeral system, which has the base 16. So this system uses 16 symbols, and we have 10 symbols commonly from the decimal from 0 to 9, and from 10 to 15 we have representation by the alphabet symbols. A is equal to 10, B is equal to 11, C is equal to 12, D is equal to 13, E is equal to 14, and F is equal to 15. The main advantage of using this numeral system is that it keeps the representation short and therefore manageable. For example, the decimal number 199834 is represented in binary as this number, and in hexadecimal it is represented in a very short form. So here is an example of the hexadecimal numbers. So 7 will translate itself to the 7, and the D will translate to 13. Rest of the rules are the similar. So at this point you may ask why we need all these systems. Well, the basic answer is that for the representation purposes of the humans. As we know, the length of the representation can grow very rapidly if you are using the binary number system, and even decimal, while it expands slowly in hexadecimal because their extra symbols are allowed. So we need hexadecimal numbers to keep things manageable on the paper. However, computers only need the binary numbers, but humans can work with the decimal, octal, and hexadecimal numbers. Therefore, we should know these systems and how to convert between these different representations. The important consideration to understand here is the representation of digit in the number system and its subsequent position. So the length of number representation grows from right to left, just like 0, 1, 2, 3, and so on. So remember, it grows from right to left. For example, if we have this number, it has the length 1, and if you grow it into the left side, it has the length 2, it has the length 3 now, it has the length 4 now. So let's take the example of a decimal system. The number 9 in the decimal consists of one digit 9 located at position 0. Similarly, all the numbers from 0 to 9 all consist of single digit located at position 0. So, but once we reach the number 9, we do not have any extra symbol to represent our next number into the system. Therefore, we reached 9 by counting the numbers from 0, 1, 2, 3 up to 9. So as you can see, for counting each number we added 1 to the previous number. So when we reached 9, we are left with no new symbols, and then if we add 1, we are unable to represent 10 as a new symbol because the limit of the decimal number is the 9th digit as maximum. Therefore, once you reach to the limit of any number, even it is decimal, octal, or hexadecimal, you start it from initial again. So the start of the decimal or even any number is 0, and you take 1 carry forward. So therefore we add another digit onto the left at position 1, and hence we get 10. And then we start up to adding 1 to each number and reach at 99. Again, we do not have any extra numbers, and we run out of two length combination symbols, and we must proceed to length 3 representation starting from 100 to so on. So in general, a number x may be represented with a representation of length n in the following manner. So here we represent the representation bp as the digit located at position p, and remember it will grow from right to left. So at location 0 we will have our first digit, at location 1 we will have our second digit. So for example, if you want to represent this number in a decimal, at location 0 or d of 0 we have 4, at d of 1 we have 3, at d of 2 we have 8, at d of 3 we have 9, at d of 4 we have another 9, and at d of 5 we have 1. So here are some terms to remember. In general, we call the rightmost location as the digit 0 or the least significant digit, and if we're doing into the binary terms, it will be used as the least significant bit, and the leftmost digit is at the location D of n minus 1, where n is the length of the number. It is called most significant digit, and if we're referring into the binary, it is the most significant bit. So a number in the binary system is represented in 1 and 0 form, and each digit in the binary system is more commonly called a bit. That means every number 0 or 1 is 1 bit into the binary system. Therefore, a bit is a single digit in a binary representation of a number, and when a binary number is represented using 8 bits collectively, the resulting representation is composed of 8 locations from D0 to D7, and these 8 locations combined are called a byte. So similarly, a binary representation composed of 16 bits is called a word. A binary representation composed of 32 bits is called double word, and a binary representation composed of 64 bits is called quadruple word. So a less common, we may have representation of a 4-bit number, which is called a nibble. So the concept of byte is fundamental in computer science because a byte is the smallest addressable unit of memory in modern computers. Furthermore, data is quantified in terms of byte. A byte is therefore a unit of measuring the data in computers. So as you have seen different kinds of representation to measure the memory, and the most common is kilobyte, which has 2 raised to the power 10 bytes in 1 kilo. So if you want to calculate how many bytes are in 37 kilobytes, you would like to multiply with the 2 raised to the power 10. Similarly, if you have 1 megabyte, you will have 2 raised to the power 20 bytes, or 2 raised to the power 10 kilobytes. For gigabyte, you will have 2 raised to the power 30 bytes, and for terabyte, you will have 2 raised to the power 40 bytes. So what if I know the digits and want the actual representation for a number from them? Assuming I cannot simply paste the numbers together, but actually I have to do the computation. So for each location, as mentioned in the previous few slides, we have to multiply the number with its base to the power of its location. So if we represented the digit of the number with d, and each number was represented with the location, so if we had the location starting from left to right, and we may have this form of number representation. So let's see, we have a 3-digit number and we represent it using 132. So 2 is located at location 0, 3 is located at location 1, and 2 is located at location 2. So for each location, we multiply it with the base power location. So 2 will be multiplied by 2 raised to power 0, plus 3 will be multiplied by 10 raised to power 1, plus 1 will be multiplied by 10 raised to power 2. So this computes equal to 100, this computes equal to 30, and this computes equal to 2. So our result will be equal to 132. So in general, the decimal system is composed of the number using this formula. So this formula simply states that for each digit location, multiply with the power of the digit location, and then sum the value from location 0 to location n minus 1, and so on. So can you use this method to convert a number from any other base to decimal? Yes, you can. So we can rewrite the above formula for any general base radix R, which may be base 10, base 2, base 8 or base 16 or anything we wish. Therefore we get the similar formula to represent the number, and again we have location 0, 2 and minus 1, and we have the digit of p, that means location of the digit, and the digit itself multiplied by the power of base uh, r into p. So let's call this the method 1. So by this method we can compute any representation of any base and find its equivalent into the base 10. Here is the implementation of the previous formula to convert numbers from binary, octal and hexadecimal to convert into decimal numbers. So can you recall the formula? If you do not, let's write it again. So we had the formula dp, that represents the digit on the location p, multiplied by the base, which was represented as radix r, with respect to the power p, that is again the location, and we will sum up the all of the numbers ranging from p0 to n minus 1. So let's see, we have a binary number which is represented as 1001. Therefore we have the base is equal to 2. So apply the formula. As you can see, for the first location or the location 0, we multiplied by the base 0, 2 raised to power 0, and for the first location we had 2 raised to power 1, 2 raised to power 2 and 2 raised to power 3 for each digit, and then we calculate their sum. So anything multiplied by the 0 will result in 0. Therefore we have two terms, 1 and 8, and it is summed up to 9. Therefore the representation of this binary numbers in decimal is 9. So let's see, we have another number which is represented in octal format, which has the base 10, and we use the similar formula, multiply with the base power location. So for the first digit, which is 7, we multiply with the 8 power 0. At location 1 we have 8 raised to power 1. At location 2, 8 raised to power 2. At location 3 we have 8 raised to power 3, and multiply with each consecutive digit. So in this case we did not had any digit represented as 0, therefore all of the terms will result the number, and then we sum up all of the terms to represent the number in decimal. Similarly, we have the hexadecimal number, which has the base 16, and which is again calculated using the same formula. Only difference is here that we have a base 16. So for the first number we have base 16 power 0. For the second we have 16 raised to power 1. For the third 2, and for the third location we have 3. So we sum up the values again, and we have the same representation of the number, but in the decimal format. So this is very easy, but how can you solve the converse problem? In other words, how do we convert the decimal numbers into the binary, octal or hexadecimal? So as you have seen in the previous example, the common thing to convert the numbers into the decimal format was multiplication with the base. However, if you want to convert from the decimal number to any other format, you have to use the division. So let's say you have to convert a number 1233 into binary equivalent. So what you are looking is to find the digits from D0 to D and minus 1. So let's say if you divide this number with the base in which you want to convert, and in this case we have the binary base, so therefore we will divide it by 2, and we will have a result in this format which will be 2q plus remainder. So where REM is represented as remainder, and when we divide this value by 2, and we get a quotient value which is q, which is multiple of 2 and some value remainder. So remainder here could be either 0 or 1 because we are dividing it by 2. So for now I will simply take it as d0. You will soon see why I am doing this. So whenever you divide that number d with the base value, the result is 2q plus d0 because the remainder is a binary digit. So let's repeat the previous process, and again if our number is still greater than 2, we will divide it once again. So in the first form we got the number d0, and if we divide the number again we will get our number d1, and similarly up to dn minus 1. So if you expand the formula by using the similar division rule in the previous slide, which was dividing the number and getting 2m, sorry 2q plus rem. So replacing 2q plus rem or digit lost we will place, you get the subsequent values, and in the case of this term we get this equation. So continuing this process, we will reach at a point where the quotient cannot be further divided. That means we have either reached 0 or 1. So at this point we will have derived the following formula, which is much similar representation of previous formula, which is the representation of the digit at location 0 multiplied by the base 2 over p. So which is exactly the same as method 1. So it turns out by dividing we are only doing the opposite operation of what we had done before. Therefore our assumption of taking the successive remainders as d0, d1 and so on was in fact correct. So generally, if we want to convert a decimal d into the equivalent number in the base r, we will simply divide the d by the base r, and then the successive quotients by the r, and pick the successive remainders as digit 0, digit 1, digit 2 and so on of the equivalent number in the base r. We call this the method 2. So for example, let's say we have the number 1234 represented in decimal and we want to convert into octal. So we will divide the number with 8 and take the remainder. So let's say we divided the number first time and we get the value of quotient 154 and we get the remainder 2. So this is our D0 or digit 0 value. So now the quotient is still greater than 8. We divide it again and we get another quotient of 19, and the digit 1 is again 2, which is the remainder. So let's divide 19 again by 8 and we get 2, and the remainder is 3. So we get third digit as 3, and finally we have the quotient 2, which cannot be further divided. Therefore this representation is the representation of the decimal number into octal. Similarly, the next example shows the division of same number with the 16 to represent this decimal number into hexadecimal format, and the representation is 4D2. Similarly, if you represent this number into the binary, you will divide it by 2 and you will have this representation into the binary, which is 1001101000001 into the base 2. So now we possess enough knowledge to convert a number from any given base to desired base. So simply we first convert the number into the decimal using the method 1, and then from the decimal to the desired base using method 2. So if you want to convert the number in base R to its equivalent number in base S, you simply follow the following path. For example, you had the number into the binary system and you want to represent it into a octal system. So you will use the first method to convert it into decimal number system. That means you will multiply the each digit with its base to the power. And then once you have the number into the decimal format, you use the method 2 to convert into the octal base. So in this case, we will divide the decimal number by 8 and keep taking the remainders, and the remainders are the actual representation of this binary number into the octal number. So here is an exercise for you to try a decimal to binary conversion. So it is a simple conversion, you just have to take the remainders. So this is again another conversion from decimal to octal. So can you remember which formula you will use here? You have to use the second method. That means you will divide the number with the 8 and subsequently take the remainders. However, if you want to take the equivalent value of the point values or fractions from decimal to octal, there is a slight modification. For fractions, you have to multiply with the base value you want to convert. For example, if we want to convert 0.05 from base 10 to base 8, you would like to multiply it with the new base and take the most significant digit. So as you multiplied 0.5 with the 8, you get the most significant digit as 0, and then again with the 8 you get 3, and then you multiplied again, you got 1, multiplied again 4, multiplied again 6. So you can continue multiplying to get the values into the fraction of the desired base. So here is another example, but it's done into the opposite direction and you want to convert the octal value to the decimal value. So in this case, you will use the first method, and which is the multiplication method. So for each value into the octal, you will find the digit locations, and for each digit location you will multiply the digit with the base to the power of that particular location. So in this case we will have 3 raised to power 80 plus 4 multiplied by 8 raised to power 1 7 multiplied by 8 raised to power 2. So we will get an equivalent value into the decimal. Similarly, you can perform the octal to decimal conversion on the same formula and check the result here. So here is another exercise for you to convert a number from decimal to octal. So these are two exercises, and do it on your own to verify these results. Here is another exercise in which you want to convert from octal to decimal. So two values are given into the octal, and both of the values are converted to decimal format, and the method is provided here. So as you can see, again you multiplied each value with its location base power. So in this case, the first value or the first digit was 1, the second was 8 raised to power 1, 8 raised to power 2, 8 raised to power 3, and 8 raised to power 4. So you multiplied each digit with its base power, and then you get these values as a result. So here is another example, which is the conversion of decimal to hexadecimal. So in this case, you will divide the decimal number with 16 and take the remainder values to find out the hexadecimal representation. This is done into the reverse direction, and you would like to find out the decimal representation of a hexadecimal number. So in this case, you will use the method 1, which is again multiplication method. So this is another example for you to calculate the decimal representation of a hexadecimal number, and in this case you have a fraction based number. So that is the end of this lecture, and if you want to learn more about the topic, go through the recommended books, or you can ask me any question. Thank you very much.